there remains one quadratic conic section to be discussed, and that is the hyperbola. Hyperbola has the geometric characterization of a set of points such that the difference of distances to two fixed points f1 and f2, which we again call the foci of the hyperbola, is constant. So any point of the hyperbola satisfies that the difference of distances from this point to two fixed points f1 and f2 is constant. So it should be noted that we do not specify if this difference is positive or negative, and in fact we have to take into account both. So the geometric condition can be written as distance from point P. So this is P is a general point on the hyperbola. Distance from P to F1 minus P to F2 is equal to plus or minus 2a. So here again, a is a positive constant. We want to put the factor of 2 in here for convenience, because it makes the resulting formula particularly simple. And we want to take the plus minus in this difference because we do not know which focus is the closest one to point P. We have two foci, f1 and f2, like so. Again, we place our system of coordinates so that the foci are symmetric with respect to the origin. And then let's say you have a point P somewhere here. It will be, of course, closer to the second focus. So then if we connect P to the two foci like so, the difference will be the difference PF1 minus PF2 will be positive. But of course, if we take a point P somewhere here, it will also belong to the hyperbola, but it will be closer to F1, and therefore the difference will end up being negative. So we can sketch hyperbola by first drawing its asymptotes. So we'll discuss a bit later what exactly the meaning the asymptotes have. For now, we'll just need it for the sketch. So the Okay, so let's move the point P a little bit, like so. And then we can sketch the two branches of hyperbola like this, shown here in thick blue lines. And then, as we just explained, if the foci are taken to be symmetric with respect to the origin, we have two branches of hyperbola, such that any point from the right branch, as shown here for P, will be closer to F2. Any point in the left branch will be closer to F1. But the difference between the distances to the two foci will always be the same up to the sign plus or minus here. So let's say that our foci have the coordinates C0 and this would be minus C0 and C0 for a positive C. It is interesting to observe that, unlike in the case of an ellipse, here the intercepts, the x-intercepts of hyperbola, which we again call vertices, so these here are the vertices of the hyperbola. By analogy with the intercepts on the longer axis of an ellipse. But unlike the ellipse, the intercepts or the vertices of the hyperbola lie between its foci. So for ellipse, we had foci living inside the ellipse, and so it was always that C was smaller than A, where A is the coordinate of the vertices. So if we denote vertices by plus minus A0, it becomes apparent what A is in this case. So it's the same A as we have in the geometric condition. It's not hard to check that if you look at the x-intercept, the distance to the difference of distances to the two foci is precisely the distance from this red vertex to the origin. That is because if you take distance from this red vertex to F1, you have this length to the origin and then another length to the focus. But the length to the focus consists of two parts. It consists of this part, equal to this part here, and the part that is equal to A. So you see that the difference between distance, I guess I have to draw it. So the distance from here to F1 is like so. Distance from here to F2 is like so. And so these two bits are equal. And so if you subtract, if you think of the vertex as your point P, then PF1 is right here, and it consists of this bit and two bits like this, which we'll show in blue, or rather green. Right, so if you subtract PF1 minus PF2, you have this red interval and two green intervals, and you subtract one red interval, that is. And so you have one red plus two green minus one red, and that gives you two green. And so that shows you that the distance from the vertices to the origin is precisely equal to A. So this distance here is precisely A. And so that's why the vertices have coordinates plus minus a0. Okay, so we have shown that this difference has very specific geometric meaning, and then our next step will be to derive a Cartesian equation for hyperbola. So using the distance formula, just as we did for the ellipse, we arrive at the following equation for hyperbola. We'll get x squared over a squared minus y squared over b squared equals 1, where the relation between a and c is different, or a, c, and b is different from the one we had for ellipse. So if you remember, for ellipse, a was the length of the longest half axis. So of three numbers, a, b, and c, a was the largest, and a squared was equal to c squared plus b squared. Now for the hyperbola, because distance from a focus to the origin is equal to c and is bigger than a, of the three numbers a, b, and c, c is the largest. So the relation here is the following. You have c squared equals a squared plus b squared. So it's easy to remember this if you think about the picture. For the ellipse, foci lie between the vertices. For hyperbola, it is the other way around. The vertices are between the foci. So that is why you get c squared is larger than a squared. And so this is the equation of hyperbola. Oriented horizontally. With foci at the points plus minus c 0 and vertices at plus minus a 0. So here, unlike in the case for the ellipse, orientation is not determined by the largest denominator, but is determined by the positive term. So here, the x term is positive, and therefore our hyperbola is oriented horizontally. If it were the y term that was positive, our hyperbola would be oriented vertically. So before we get to that, though, we need to mention asymptotes. So hyperbola has this interesting pair of lines that it approaches when p goes away from the origin. So when the point p here goes very far away from the origin, it approaches one of the two lines shown here in dotted blue. So let us obtain the equations of these two lines. So in order to do that, you have to think like so. So the asymptotes correspond to very large values of x and y. So this means in the equation x squared over a squared minus y squared over b squared equals 1, 1 is much smaller than the other terms. Consequently, it is negligible. Right, so 1 is negligible compared to the other terms. But without it, we get the following equation. So without 1, we get x squared over a squared equals y squared over b squared. And this is precisely the equation of the asymptotes. Right, so basically, in order to obtain the equation of the two lines, you say, well, okay, when x and y are very, very large, 1 basically does not count. And all that matters is this difference. So this difference is approximately 0, right? Because 1 is so small, and all that matters is this difference of two very large terms. And since 1 is negligible, you rewrite this equation in this form. And I should, in principle, write this not as an exact equality, but as an approximate equality. But still, the way to arrive at the equation asymptotes is just write this with exact equality and say, well, this is the equation of the asymptotes. In other words, it's an equation of a pair of lines. Right? So to see that, you just have to solve it. And if you solve it, you have the following. So if you take square root of both sides, you see that y over b is plus minus x over a. And so the equation of asymptotes is y equals plus minus b over a times x. And so this is the equation of the two asymptotes to this hyperbola. I'll just summarize what we have said so far. We're saying that the equation x squared over a squared minus y squared over b squared equals 1 is a horizontally oriented hyperbola with, as we already mentioned, the foci at the points plus minus c0, vertices at plus minus a0, where the relation between a, b, and c is the following. We have a squared equals b squared plus c squared. Whoops. Aha. It's actually the other way around because c is larger than a. So we have this relation. And let's see. And then asymptotes is what we're missing here. Asymptotes y equals plus minus b over a times x. Okay, great. So this summarizes all that we have learned about this particular hyperbola. Now, as usual, we want to interchange x and y and get a vertically oriented hyperbola. So let's do that. So interchanging x and y gives this equation. Let's indeed interchange x and y, like so. And this is a vertically oriented hyperbola. With foci 0 plus minus c, vertices 0 plus minus a. The relation between a, b, and c remains unchanged, and the asymptotes are so if you just directly interchange this, you get x equals plus or minus b over a times y. If you solve for y, you get the following. Alternatively, you can think of this equation as obtained from this here by, again, saying, okay, well, 1 is much smaller than these two terms, so it is effectively negligible, and you have y squared over a squared minus x squared over b squared equals 0. You solve that for y, and this is the solution of that. So you basically can obtain equation of the asymptotes of a vertically oriented hyperbola by the exact same argument we used for the horizontally oriented one. Great, so we have now obtained the equations for hyperbola. And we can again ask questions of the kind, given certain geometric information about hyperbola, derive its equation, and vice versa. Given its equation, derive some of its geometric properties. So let's give an example, such a question. So this will be example 3. Let's say we will start with some geometric information and work our way towards the equation. So let's find the foci and equation of the hyperbola with vertices 0 plus minus 1 and an asymptote y equals to 2x. Okay, so this problem doesn't give us two asymptotes, it only gives us one. But of course, this is not very clever because we know that the asymptotes have plus or minus in them, and so it means that the asymptotes must be of this form, y equals plus minus of 2x. And so this is equal to plus minus a over b or b over a times x, so we have to determine which it is. So let's look at the vertices. We see that the vertices have the same x coordinate but different y coordinates. So the vertices are oriented vertically, one above the other, like so. And so this means that we have a vertically oriented hyperbola. And so looking at the case for the vertically oriented hyperbola, we see that the equation of the asymptotes is plus minus a over b times x. So that's what we put here, plus minus a over b times x. So we know the ratio between A and B. Okay, good. That's one piece of information. In fact, we have more. So we know that A over B is equal to 2 from this equation, but we also know that A is equal to 1. Since vertices have the equation 0 plus minus A. And comparing this expression to what we have for the vertices, we see that A is 1. Great. So this allows us to conclude that B is 1/2, right? Because we know that A is 1, the ratio A over B is 2, and therefore B must be 1/2. Great. So we have the value of A, we have the value of B. We can now derive the value of C. And so we know that C squared is A squared plus B squared. Remember that in this case, foci are further away from the origin than the vertices, and so C squared is the largest of the three. And this gives that C squared is equal to 1 plus 1/4. And so C is square root of 5 over 2. And okay, so this means we can answer the first question of this example. We can determine the foci. Since it is a vertically oriented hyperbola, the foci have the coordinates 0 plus minus C, which is 0 plus minus square root of 5 over 2. Furthermore, we can write down the equation of this hyperbola, because we already have A and B, plus we know that it's vertically oriented. Great. So let's use that. We know it has the form, since it's a vertically oriented hyperbola, the y term comes with a plus. So we have y squared over a squared minus x squared over b squared equals 1. And it just remains to put in the values for a and b. And that gives us y squared over 1 squared minus x squared over 1/2 squared equals 1. And that is, of course, y squared minus 4x squared equals 1. So this is the desired equation of our hyperbola. So to summarize, in this question, we started with some geometric information about the hyperbola. We were given its vertices and asymptotes. And then using that information, we worked our way towards determining the equation. Of course, we could have gone also the other way around. We could be given the equation, and using the equation, we could determine the geometric properties of a hyperbola using the information given here.